Hello, good afternoon. Welcome to another session of Wildlife Analytics. Today, we will be going through the EDA, which we have discussed in the previous session. We have seen the concepts. So today we'll be working with the code of how EDA works for a data set. So first, it is very important to import necessary libraries to import the read the data set. So first here I'll be okay. First here I'll be importing pandas since it is necessary to read my CSV file. And then here the data set data which I have taken is the tick distribution in the cattle. How the tick is distributed and what are the components we have in them. So let's go and run this code. Okay, we have an error. There's no such file or directory. Okay. So what we'll do is we'll just remove this. Okay, so it should work now. Yes. So here to for the tick data set, to identify the problem statement and its objectives, they have come up with a data that is very useful to determine the distributions. So here they have taken day, what day it is. They have calculated the value or distribution of tick per day, and with respect to its season. Season wise, we have approximately 3, but 4 seasons. So in first season, they have taken the number of days. Season is almost up to 3 to 4 months. So 4 months data equals to a day. So, and these are the farms. Farms as in the cattle and ticks in an area, in a particular geographical area, there are many farms who are farmers who takes care of cattle, either for their agriculture purpose, either for their own benefits, or either for selling. So these are the farms that are there. Okay, this total of 1,290 rows and 9 columns. So the columns include day, season, and farms. And year tag number. What is this year tag number? Year tag number is nothing but the tag or a number given to a single cattle to identify them. This year tag number, it not only contains a number, but it also contains its sex, age, stocking density, body condition score, and tick distribution percent. Okay, each cattle, or you take one cattle, how much percentage of tick it has. So the year tag number, it has its specific number, that is 43, 45, 23, 34. And these numbers, as you're seeing here, is 45 and 45 is repeated because these both are not from a single farm. Okay, the farm name is Totak, and the cattle they have picked is the number 45, and There's another farm with the name Icha, and they have picked the cattle with the number 45. So that's why the numbers, the year tag numbers are repeated. But as you see, the farms are completely different. So here, another thing to remember is from each farm, for each season, one cattle is taken to identify the stick distribution, score, stocking density, etc. So the sex of the animal also depends on the tick distribution and its age. Is it old? Is it young? Or is it etc. So stocking density is the stocking density of the wool it has. If you take a sheep, it has a lot of wool. So this is the stocking density of it. And body condition score, overall body condition, if it has any diseases, if it has any conditions about illness conditions, or if it is healthy. So 1 determines it is healthy, and so on up to 9, it determines that it is very ill. And tick distribution percent. This is the distribution of ticks in their stocking density of the cattle. So we have a total of, sorry guys. We have a total of 1,290 rows and 9 columns. So now next, info. It gives us the info of the distribution. That is range index. That is, we have 1,290 entries. That starts from 0 to 1289. You can see here 0 to 1289. And data columns, we have a total of 9. Those are day, season, farms, year tag number, sex, age, stocking density, body condition score, and tick distribution percentage. So here, this null, not null count is nothing but how many null values you have in your data. Here, as you can see, not null means there are no null values in the data. And then here comes the data type. D type is a data type. Here for day, it is int. Season, it is in a categorical form, so it is an object. Farms is also a categorical data, so it is an object. And year tag number is int, etc., etc. Except for sex, which is a male and a female, all are with int. Then here is the count of each of these D types. That is, int, how many are there, and object, how many are there for our data. So here we have int 64, that is 6, and objects are 3. 1, 2, and 3. Okay, and the memory usage for this particular data set is 90.8, more than 90.8 KB. Okay, so now we are importing NumPy to calculate the mean, median, mode, that is statistical analysis, which is nothing but the exploratory data analysis, that is measure of central tendency, first moment business decisions. Here the dot is used to refer to the variable within object. Here the tick data has this distribution percent, and for that you have to do the mean of it. Get the mean of it. Okay, that is how it is read. So here tick distribution percent, they're telling us to find the mean. So the mean from the whole data for tick distribution percent, this is 43.66. And then the median is 45, and the mode, which is the most repeated, is 45. Name will be the tick distribution percent for this data type is int. Okay. This is the first moment business decision. Here you can also get a stats.mode. The same way, the mode, to find out the mode, this is also another technique. Okay, here the stats is not defined. Okay, let it be. We'll not look into it now, because we already have the output. Okay, next is the second moment business decision, that is measure of dispersion. We have here variance, standard deviation, and range. For that, we take tick distribution percent dot variance is 235.80, and for the standard deviation, which is 15.35, and the range of it is 65. So here the range is nothing but taking the maximum of the tick percent minus the minimum of the tick percent. So subtracting the maximum minus minimum to get the range. And then we have third moment business decision, that is skewness. So the value of skew is minus 0.05, which is negatively skewed data. Okay, so and then we have fourth moment business decision. For this, we have minus 0.25, which is also a negative data, negative kurtosis. Here we have some of the visualizations. Okay, here EDA we have two parts, that is statistical analysis. Next is a graphical representation. So here comes a graphical representation. Data visualization. Import matplotlib pyplot as PLD, and we can also import Seaborn as SNS. So we want to first know the shape of the data set. That is, we have 1290 rows and 9 columns. And then we have pld.hist tick season. We want to see the season with which the data is distributed. So we have summer with a count of almost 350, or take it 340, and rainy also almost 350. And spring, we have less thick distribution, that is 300. And winter, we have a little about the spring. So this is the distribution of thick with respect to season. This is a univariate data with one column. Next, we have a univariate data, that is box plot. Here, it will help us to check, box plot will also help us to check the outliers that are present in the data. Okay, as box plot is also a univariate data representation, it will also show us the box plot, also shows us the outliers in its respective data. So as you can see, we have did it with thick percentage and it doesn't have any outliers to it. So here visualizations come to an end, but I know there are a lot of visualizations for the bivariate and multivariate. We'll be looking at them when we are going further. So as we understood our data now, we learn what anomalies we have, if there are any missing values, if there are any outliers, if there are any duplicates, etc. So to get the accuracy of these, we have to eliminate the data. Data pre-processing, first is a typecast. We take the data, and see its types. That is date, season, farms, year tag number, sex, age, etc. So it's data types that are 8 and objects. So here we are taking a column of future, that is talking density, which is an int, and changing it into float. So take the talking density as type as float. So take dot types as float. That's changed into float. So that is how you use typecasting. Here, the second method is to identify the duplicates records in our data. Duplicate is equal to tick dot duplicated. So we are trying to get the sum of all the duplicates that we have in our data. So let's see. The duplicates we have in our data is 0. Okay. If you want to try it out, you can just put some duplicates in your data and then try it. So if you have, suppose if you have duplicates, as I have 10, then how do you remove those duplicates? You use tick dot drop the data set, and then you use the command dot draw duplicates and drop duplicates. Okay, this is how you drop. That is about typecasting and duplicates. Next is outlier treatment. First, we import Seaborn as SNS to see a better and colorful graphs than plots. As you saw here, the plot for the box plot, if we use matplotlib, is very plain and dim. Sorry. But after we import Seaborn, we can see the box plot has more color to it and it shines out what the important parts of the box plot. So this box plot is done for the data day, which is in our data set, to find any outliers are there or not. So likewise for year tag number, where we see there are no outliers, and also age, and then stocking density. As we can see, there are some outliers here. The single dot which is here is the outlier. And next is the body condition score. Yes, you can see this also has some of the outliers. And I didn't do it for tick distribution because we already did this here, tick distribution first. Okay. So after checking for the outliers through a box plot, we move on to eliminate those outliers from our data. First, to do that, we have to detect of the outliers. So for that, what do we do is we find limits for stocking density based on IQR, that is interquartile range. So IQR, which is an interquartile range, has quantile, limits, etc. So we have lower limit, upper limit, and we have quantiles. That is 0.25, 0.75, etc. So how do you do the outlier rating? We have techniques. As we discussed yesterday, there are many techniques, but here we have done one. So it's a 3R technique, that is remove, replace, and rectify. And then we have something called as vinsorization. What does it do, vinsorization? It takes the values which are here above 95 and put it into the 95 and above 5 percentile to the 5 percentile. So to do that, before we have to set the limits, that is the data set tick. For that is a stocking density. Here we have only outliers for stocking density and body conditions. So that's why we have here the stocking density. And for that, we doesn't know where the outliers are. So we are putting it in the quantile of 0.575 and minus in the quantile of 0.425. And then if it is a lower limit, quantile of 0.25 minus IQR into 1.5, and upper limit, take this the data set with the column which has an outlier with a quantile of 0.75 plus IQR into 1. So this is how you set the limit. After setting the limit, with the help of these limits, we trim the data set. This is also called removing, is also called a trimming. So first, let's see how many outliers are there in our data set. Okay. Okay. Maybe I have to split it out for you guys to understand. So we have for the stocking density a total of 43 outliers. Then we trim these outliers and get the shape of them. So here 1290 is the actual data with outliers, and after trimming we got a data of 1247. So that is how you trim the data. And then you replace the trimmed data. So you use a data frame tool where numpy is used. Numpy np.where you give a condition that tick and its stocking density is greater than the upper limit to the upper limit, and then to the lower limit less than the lower limit to the lower limit to tick density, stocking density. Okay, so it gets replaced, the data gets replaced. After that, you have vinsorization. This is how it gets replaced. This is the data. The stocking density. We have an outlier. The total of that outliers was 43. So now we don't have any outliers for the data. This is one method of doing it. Another method is the vinsorization method. Okay, where you have to install the package from feature engine.outliers, import vinsorizer. So the capping method here we have taken is the IQR, and the tail is both left, right, or both tails. It depends on what we want. Fold is a 1.5 fold, and variables with the stocking density. So tick is equal to vinsor.fit transform tick of stocking density. And then you see the plot. So the plot that you get is this one. Either you can do this method if you have outliers in your data, or either you can do this method. But defining the limits is compulsory. That is for the stocking density. And this is for the body condition score. So for the body condition score, also you follow the same steps. You first get the limits and then you trim the data. That is to you remove the outliers from the data, or you get the sum and then you remove it. After removing, you replace the data. Or either you can use the winsorization from feature engine.outlines. Okay, first you have to import feature engine. From there, you can take the outliers, feature engine.outliers, which has a winsorizer. So then you fit it. As you can observe, we don't have any outliers in it. And the next is the zero variance or near zero variance. So we'll check if we have any of the zero variance. So what is zero variance? If the variance is low or close to zero, then the feature is approximately constant. Okay. And will not improve the performance of the model. In that case, it should be removed. That's why you eliminate zero variance or non-zero variances or near zero variances. So first you check for variances and then see if the variance is zero. So you have it here. Day, year tag number, age, stocking density, body condition, tick, distribution, tick replaced. Okay. Tick replaced is also given because there are some of the things that are replaced. So all of them are false, meaning there are no near zero or zero variance. And then we have discretization. First, we describe. This is the describe we got. Okay. Then we cut the data into bins. Minimum, tick dot stocking density, and then we get the mean, and then we get the maximum, and then you set labels for it as high and low. And we have to include the lowest number, that is, if we are telling them to include it as true. So, and then we get the head of it. Tick stocking density, this is a new. We are asking for them the value counts. Okay. So these are the value counts which we got. Okay, I can split it up for you guys. Just give me a minute. Okay, here is a describe, that is count, mean, standard deviation, minimum and maximum, and 25, 50, and 75% for all the features in the column of the column. Okay, so then you get the new stocking density, that is with respect to stocking density. If it is 40, it is low. If it is 50, also low. If it is 90, then it is high. If it is 100, also it is high. 75 is high. Okay, it will divide it into ranges of 25, 75, and 50. Okay, so And then we have pick new value counts. That is low, we have 688, and high, we have 602. So the name of it is stocking density new. Okay. So stocking density with values. This is for the old one. I think so we got the output here. This is nothing but for our data set. We have 90 number. It's 120 times repeated. 100 is 129 times. 50, 129. 20 is 43 times, like that. But since we made it into two variables, low and high, we got the total count as 688 and 60. Then we have dummy variables. Here are the tick columns we are telling to show. And then tick new query.get dummies. And then get dummies, tick drop first is equal to true. We are telling them to drop the dummies. Or we have created dummies for all the categorical columns. So with dummy variables, we have one hot input. In one hot encoding, we are telling them to divide it based on seasons. So for that, we have to import sklearn pre-processing. We have to import one hot encoder. So this one hot encoder, we have to fit it into the data frame. And then we have to give the values for which we have to do the encode. Okay. So this is about the pre-processing steps. We have missing values, we have imputation and all. So these missing values and all will be seen here. So by the time this loads, let me explain to you this EDA. This is something called as auto EDA, where the EDA which we did up, all the statistical and graphical, that's this in just a matter of 2 lines. Where we took half a notebook, yeah, it just did it in a single block with just not more than 8 words. Yes, we just have to import, and then we have to assign a variable to it, and we have to get the report. What report you want? The data, and you're giving that data. That's it. So I think so it's loading. It's loaded. Okay. Now there are many types of EDA, but we'll be seeing or looking into 2 EDA processes for now. So here it's summarizing the data set which you have given, that is tick. It's summarized 100%. And it's generating the report structure, which is 100%, and render HTML. Okay. It's giving out in a HTML. So This is the pandas profiling report of our data set. Okay. So the data set, this is a statistical analysis of our data. The data set statistics. Okay. We have number of variable is 1. Okay. Number of observations is 1290. Missing cells, we have none, that is 0. It gives you the percent. If you have a number of 100, it gives you the percent. Okay, it can be 100. So take missing values out of 1 to 100, it is 40. So here it will give you the missing value cells percent as 40%. Okay, you can see down for the duplicate rows, it is 4. So here the duplicate rows percent is 0.3%. So even for the missing values, that is how the output is. So total size in memory is 10.2 kilobytes and average record size in memory is 8. So how many variables do you have in a categorical? That is 1. Okay. So here, okay, I think so. We have selected only season. So that is why it is only showing a season. But what we'll do is, we'll come back to it after refreshing the kernel. Okay. Then now we have to import the data. Okay. Now again, we will load it. I think so. Yeah, you should have got an idea when you're showing variables are loading this. So it's okay. Okay, here it is. You get the summarizing the data. Okay, we got the output. So the number of variables we have are 9, and numeric variables are 5, and categorical variables are 4. Excuse me. Okay. So here the missing cells is 0, duplicates are 0, and total size is so much. So here we have the variables in the column, in the data. So we can select the data. Here we have all the columns in our data set. We can select it as and when we want, what is one we want to see. Distant is nothing but unique. So we have 1290 distant values. That is the whole data set we have. And here, this is the day. So we have minimum is first day and the maximum days is 1290. Here zeros represent to the variance. So we have no zero values and then missing no, infinite no, mean of it is 645.5. Okay, here it is day is a real number. There's something wrong with it. Just give me a minute. Sorry, sorry. So day, which is a real number, and uniform and unique. It is unique. So if you want more details about it, we can get the statistics. This is the quantile statistics, descriptive statistics. For this statistical analysis, that is first, second, third, fourth business units. Range, median, mean. Yeah, we have standard deviation, variance, etc. Skewness, kurtosis, all of them. And we also have the graph of it, that is a histogram. Here the fixed size bins, they have taken it as 50. And the common values are this. And the extreme values are this. So that is how you read it. And this is a categorical data which has season in a categorical form, distant of 4, missing is 0, and we have the distributions as summer, rainy, spring, and winter as its number. So if you want to see more, yes, we have it. Maximum length, mean length, minimum length, and then total characters and what it contains. Here are the categories. And here are the plot, common plot. That is how much percentage is distributed in the data. This is nothing but the word in word writings. Summer, rainy, how many are there? And then the characters. So this is about the category. And it even shows you whether it has high correlation or uniform correlation. Year tag number, sex, age, stocking density, body condition. Here it has some missing 0 values. So it is shown that it has 43 0 values. And it is 3.3%. And tick distribution. And then here are some interactions. Interaction with each other. This is a bivariate day. Okay, the graphs. You have day and you have tick distribution person. Or if you want body score with tick distribution person, also you get. See, body condition score with tick distribution. It is a scatter plot. As we discussed yesterday, for my bivariate, we always get a scatter plot. And then with body condition score, we get it as stocking density. We can say that the stocking density, if the body condition score is good, the stocking density will be more. The wool will be more. We can check if it is more or not. So that is how we use a bivariate. Then we have multivariate, where we use pair plot, heat map, etc. These are the heat maps. Okay. It shows you the description of each of the heat maps. That is Spearman, Pearson, Kendall, Camels, and Fix. Okay, with all the variables, with all the features in the column. Day, season, farm, etc., etc. All of them, with all of it. Okay, here are the count of the missing values from the data. And then this is the sample. First row, it's a head, and this is the tail of the data. Data or tail. So this is about the EDA, that is auto EDA. And then similar to that, we also have another library, auto EDA library, that is DK. So let's see how this also represents this. gives us that. Here we have given it in the d.open browser. So it opens a browser, this one. So here it shows that we have 9 columns. Here it shows that we have 1 to 9 rows. So if you want to get a description of each of these, you have to go here. Just click on season and we can hide it, delete it, we can rename it, we can replace it, we can do the type conversion, that is typecasting. We can clean the column, we can see the duplicates, we can describe, and then we can also format. So these are all the EDA steps we have. Okay, first we'll see the describer. This is how it is described. So here is the graph: rainy, summer, spring, winter, and its values. Here it gives us rainy has 344, summer has 344, spring 301, and winter 300. That is how the data is distributed. And value counts is also the same. Okay, and then we go to farms. So the describe is maximum character, unique values, and then most frequent words, minimum, average, maximum, standard words. Okay. So, and then the graph. This is a graph. This is ordinal. So we can choose a column and aggregate it. Aggregate is nothing but sum, mean, median, mode, etc. And what to do here is cleaner is nothing but we have to remove hidden characters. We can just give whatever we want. And then is the value. Okay. It works for all the columns. Male and female. Tick distribution. So it gives you here. If you click on that column, tick distribution %, it's an int format, and the skewness of it is 0.05, which is fairly symmetrical. And you can click here what it means. So here you get it as fairly symmetrical, means skewness is between 0.5 to 0. Minus 0.5 to 0.5. Moderately skewed, skewness is between -1 and 0.5 or between 0.5 to 1. And highly skewed means skewness is less than -1 or greater than 1. Okay. So we can look out for kurtosis too. Here the kurtosis is -0.26, which is a platypurtic. But what does that mean? Leptokurtic, meaning more than normal distributed height, that is kurtosis is greater than 3. We got it in negatives. So mesokurtic is normal distributed, kurtosis is equal to 3. Platykurtic is less than a normal, kurtosis is less than 3. So we got the values that are less than 3. So that is platykurtic. Okay. So for body condition score, it is 0.11, that is the platykurtic, and -0.75, which is moderately skewed. And outliers we have here as 40. So this is how you do the EDA with, or you can say this is auto EDA, which shows you all the things what and all you also can export the code for this particular thing. Okay. So you all can try this out for any of the data set just to experiment it. Okay. Since we are done with the EDA and pre-processing, we'll now move on to our unsupervised learning algorithm with a data set, that is k-means. Okay. Just give me a minute. Okay. So we'll be continuing with our unsupervised learning, that is k-means. So what exactly here K means is okay, first of all, let's see the agenda for today. We'll be learning about what is unsupervised learning. I know we already did that, but still we'll revise it once again. And then we'll learn what exactly is clustering. And K means clustering. What does K and means and clustering mean? Its advantages, limitations, key concepts, and a use case with respect to the K means. So let's start off. Here, the data stored in the database, that is the historical data, is taken and perform EDA and pre-processing. And with the help of K means clustering, which is a unsupervised machine learning algorithm, we get some output or insights. Those insights are called as rules and patterns. These rules and patterns are kept aside, and for a new data which is collected now regarding the same, EDA and pre-processing, which is compulsory for anything, and the rules and patterns of the historical data, and the K means clustering of machine learning algorithm combined predicts the output and then gives the output. That is the form. That is the predicted output. So here, when we do the machine learning algorithm, we don't get the exact output. We are always going to make predictions. Okay. So this is where, this is why we are doing it here. So based on these predictions, we get some predicted outcomes. Now the unsupervised learning algorithm is complete. If we get the predicted outcomes with the highest value, that would be our predicted outcome, exact predicted outcome. So next is unsupervised K-means cluster. So here, the points to remember are unsupervised learning is a machine learning technique in which the models are not supervised using a training data set. Instead, models themselves find the hidden patterns and insights from the given data. it can be compared to learning, which takes place in the human brain, while learning new things. So the goal of unsupervised learning is to find the underlying structure of the data set, group that data according to similarity. As you can see here, and take the example, this is an unlabeled data. We have some data points scattered here and there. But after done with the k-means clustering, we got the labeled data. Meaning this group is divided into a group, this as a group, and this as a group. So we have a X, that is a centroid. And we have to represent that data in a compressed form. So the resultant group clusters will have low variance. It all depends on overfitting and underfitting, variance, bias, etc. So first of all, what is clustering? We know how k-means work. We have unlabeled data. We use k-means and make it into labeled. But what is clustering? For unsupervised learning, Y is unknown. As we do not know why, we try to find patterns in the data or rules. We try to make sense of the data collected. As we are talking about unsupervised learning, we have something, we call that something as clustering. Here clustering is used to create clusters. How does it create clusters? By taking the data, we try to create the input groups. These are the input groups. And try to make sense of those input groups. In clustering, there are two types. One is hierarchical clustering, and the other is k-means. So today, we'll not go and look into hierarchical, but we'll deal with k-means. But I'll give a brief intro of what that is. So here, hierarchical clustering is a form of clustering which does not work when the data set is huge. Okay, first point. And the data is huge. It supports small data sets and gives better accuracy. So, but it supports small data sets and gives better accuracy. Aside, so that this is about k-means. So here, why do we not deal with hierarchical clustering? When we talk about k-means, okay, a hierarchical k-means, and beside that, there are also association rules. Which is basically creates rules on association based on recommendation engine. And we can do also consider network analytics. Best example for it is LinkedIn. And okay, other is text mining. These are main unsupervised techniques. So for now, let's see about the cluster, k-means cluster. I just clear the screen. Okay. K-means is one such unsupervised learning method that aims to group data points in clusters. So the main aim, k-means, aim of it is to group similar data points in clusters. It allows us to cluster the data into different groups. And a convenient way to discover the categories of group in a unlabeled dataset on its own without the need of any training is centroid based algorithm. So here what happens is each cluster is associated with the centroid. As you can see the above here, each cluster, this is a cluster, each cluster is associated with the centroid. Okay. The main aim of this algorithm, so the main aim of this centroid based algorithm is to minimize the sum of distance between the data points. And their corresponding clusters. Okay, so here we use k-means for large data sets and to get accuracy of the large data sets. And the main aim is to group similar data points in clusters. To group these similar points into clusters, we should have something called as centroid. So we use here the centroid-based algorithm. Where the aim is to minimize the sum of distance between the data points and their corresponding clusters. So in k-means, k is just a random value, and mean here represents the division of groups based on mean. So this is basically k-means cluster. Here, if we take a data set, it is going to get divided into several clusters. Suppose if we consider this data set, this is getting divided into several clusters, right? Like K1, K2, K3, and so on, Kn. This is a small data set, but if k-means supports huge data set, yes, so it works well with huge data set. So then you want K1 to Kn values, depending on how many clusters we want. Okay, then here K becomes 1, 2, 3, and so on up to n. So we take the existing data points and train our model to understand this data points. And based on those data points, we make the patterns. Okay, I'll explain again. We take these existing data points and we train a model, that is centroid-based algorithm and k-means clustering algorithm, to make a model understand the data points which we have. And based on the data points and how it understands, the model will automatically recognize the patterns and then divides them into clusters. How it divided? Like green, red, and so here we are segregating the data into clusters. I'll give you an example of the use case. We'll be using it for the k-means, but let me explain the concepts, then I'll go with the use case in the final step. Okay. Hope you all understood the k-means. There are other concepts which you will have to look into. I'll quickly go through the statistical side of the k-means, then we can move on. So here we have k-means does two calculations. So what are these two calculations? Is within sum of squares and between sum of squares. So what is WSS? This is nothing but within sum of squares. So that means distance from centroid for every data point in a cluster. So here within sum of squares is nothing but you have your x centroid and this distance, this distance, this distance, and this distance. So distance from a centroid, which is x, for every data point in a cluster. So this is a cluster and its data point distance. So that is WSS. Suppose we have a data point and which the cluster, it is closed to it. Suppose we have a data point here. Okay. And this is the closest data point, and this is the red cluster, which is the closest data cluster. Yes. And the data point is close to this cluster, red cluster. So this red cluster takes in this data point into it and makes it a point in it. I don't know what is happening then. Just give me a minute. Okay. So even this also measures the distance. So this method continues until all the data points form or takes all the data points are taken into different clusters. So if you have a lesser WSS, then more tightly packed the cluster is. Okay. If you have more WSS within sum of squares, the less tightly packed the cluster is. Then next we have BSS, between sum of squares. So here it is the distance between each cluster so the difference between the cluster should be as far away as possible from each other. So this is the difference between the WSS and BSS. BSS is the distance between each cluster. The difference between the cluster should be as far away. This cluster to this cluster, this cluster to this cluster. So here, BSS is the difference between the cluster. We also have something called as T. SS. That is total sum of squares. That is nothing but within sum of squares plus between sum of squares. Total within sum of squares, which is basically within sum of squares plus between sum of squares. It is the total distance between them. That is WSS and BSS based on which we get some of the clusters. So this is everything about the unsupervised learning. K-means, clustering, all that. Okay. So after all the calculations are done, it gets done independently when the algorithm is fast. And the only thing that has to be mentioned is the K value. How many clusters a data set should form? That has to be done manually. So next is the steps involved in K-means cluster. We have to first initialize a centroid K. After we get the data, we have to initialize centroid K. So after initializing centroid, for each sample in the set of samples, assign sample to its closest cluster. As we saw in our data set, we had some points here and they were grouped into the clusters. K based on the Euclidean distance. The Euclidean distance is x1 minus x2 square minus, whole square and then root. So this is the Euclidean distance. For each sample in the set of samples, assign sample to its closest cluster K based on the Euclidean distance. And for each cluster in the set of clusters, we have to recalculate the cluster centroid based on the mean of the samples in the cluster. That is nothing but K means. We have to recalculate the mean. Based on that, we have to give the K values for each and every clusters that are formed. So we have to repeat step 2 and step 3 until a stopping criteria is fulfilled. So then next is to determine the variance of each cluster and sum, that is SS, sum of square errors. We have to repeat steps 1 to 5 with different initializations of the cluster central positions. So these are the steps that involves in K-means cluster. Next is the advantages of K-means cluster. K-means clustering algorithm is used to group unlabeled data set instances into clusters based on similar attributes. So here K-means is the most used clustering method, largely due to its computational inexpensive. The computations of K-means is very inexpensive. And it can scale well with large data. It is an appropriate method when you know the number of clusters is to be drawn from the data set. So if you doesn't know how many clusters to be drawn from the data set, then you might face some of the errors. But if you exactly know how many appropriate numbers of clusters you have to draw, this would be a very good method to follow. And then the speed. Here you tell that it is computationally inexpensive. If it is computationally inexpensive, then the computation of the model is also good. That's why they use K-means the most. Okay, that's why they have mentioned the speed. And limitations. Here, the number of clusters must be chosen upfront, whether it is K is equal to 1, 2, 3, and so on up to n. You can't choose as you go on. It has to be chosen before. For that, you have to have a very good idea of your data or how many clusters it is possible to split. Outliers can have a strong influence on results. If you have outliers and your TDA and pre-processing is not done properly, it will have a very strong influence on your results. So initial centroid position have a strong influence on results. Initial means the first centroid position around the data has a very strong influence on results. So does not cluster well with clusters of varying sizes and densities. If it has varying sizes and densities, the k-means clusters does not cluster well. We have some of the key points or concepts revise. For stability, we have to run the k-means clustering multiple times. Because suppose say for a data set, we tell that k is equal to 3 clusters are enough. But if you have mean more and you want to have more and you run the program and you realize that your clusters k can have 5 clusters. So what happens then? We have to run the code multiple times. Okay. And then after 5, you realize you can have 6 and then 8. So it goes on. That's why to get a stabilized output or accuracy, we have to run the k-means clustering multiple times. So what happens then is, and these multiple times running in a cycle is called iterations with different random chosen k values. These are randomly chosen k values. This will address the multiple local minima values. So this scenario will address the multiple local values. Okay, this is the first point. And then the second point is a data point might keep oscillating. Between two clusters. Suppose say there are near clusters and it's in the middle of it. So whether it goes to this cluster or whether this data point will go to this cluster. That is nothing but data point might keep oscillating between two clusters. In each of the runs and algorithms will enter infinite loop. So how to address this? We can address this by choosing convergence criteria or by specifying maximum number of iterations. So this is how you deal with a data point which is oscillating and which gives you the loop, infinite loops. Okay. So here we have something called as convergence criteria. What is this convergence criteria? Convergence criteria is to stop when a cluster centroid moves less than a certain percentage of small distance between any of the centroids. Okay, this is the convergence criteria. It is to stop when a cluster centroid moves less than a certain percent of small criteria distance between any of the centroids. Next is, so for that, we have to compare between clusters cluster variation to within cluster variation and typical observation function used in sum of squared errors. Okay, so these are the key concepts and points to remember, or you can face some errors when you're dealing with a k-means cluster. So tomorrow we'll look at a use case and the data we are dealing with the code of how k-means clustering works. Okay, so I'll be stopping the share. Thank you very much.